So far we've talked about a lot of things. I hope you've noticed that we really haven't generated much new laws of physics. We've been using basically Newton's laws and conservation laws. Even when we discuss fluids, we're using them. And when we discussed rigid bodies, we use them. So we're not using any new laws of physics. We're still using basic classical mechanics. That's what we're doing. We're just applying it to many different areas. So now we're going to apply it to yet another area. In other words, we're going to look at oscillations. So we've looked at springs, and we saw what the total energy of a spring was, and we know what the force on a mass connected to a spring. But we have not yet discussed how that mass connected to a spring moves. And you might say, why should I discuss that? How many times do physicists look at masses at the end of springs? Actually, not very often. All right? Probably only in an introductory physics course like this. But it turns out that the same analysis that you use for masses at the end of a spring are used all the time in physics and are one of the most important kinds of analysis that we have. And right now, I just want to explain why that is. Essentially, whenever you see things oscillating, like a pendulum moving, or you might notice some wire on a telephone pole vibrating, anything that vibrates, anything that oscillates, basically boils down to what we're going to discuss right now. All right, now why is that? All right, so the answer is the following. All right, so we're going to be discussing oscillations. Imagine that I have a potential energy curve that looks something like this. I don't know, it could look like anything. You can draw any one you want. If you have a system like that, usually, due to friction and things like that, the particle will be down here. It'll be sitting at equilibrium. So for example, all your books, everything, your bodies are sitting at equilibrium right now, right? You're not moving around. I can perturb that equilibrium, and what will happen is the system will oscillate. All right? Now, why is that? The reason is I can look right around here, and I can always draw a little parabola here. Not a very good drawing. I can draw a better one. So I'm going to draw it in a different color. But what I'm doing is I'm drawing a parabola right here, such that right here, right around there, the parabola and the actual potential energy curve are pretty much identical. You know, if you take any curve in the world and look at a small enough segment, you can replace it by a line. Similarly, you could do even better and replace it by a parabola. A little section of the curve can always be replaced by a parabola. Particularly important is the section at the bottom here where it's at equilibrium. So for example, let's say right around here, the potential energy as a function of x. So I actually drew it carefully. So this u of x is this curve here. All right? It has its minimum right at 3.6. And this little distance over here is 1.65. So if you look at this part of the curve looks like the spring potential energy. So this thing here is like 1/2 k x minus x equilibrium squared. So if I look at that, that says I have an effective spring constant, k effective, 1/2 k effective, equals 2.40, or k effective equals 4.8. All right? In the appropriate units. All right? So whenever you have an equilibrium spot, almost always, there's a few very odd cases where it's not true, but almost always you can fit a parabola there, and therefore small oscillations are just like the spring. Okay? And it's for that reason that we want to treat and discuss the spring in some detail. Because we can use that, we can use the results we get from that in lots of other problems. So I want to analyze the motion of a mass at the end of a spring. So the basic idea is we have a mass m, we have a spring with a spring constant k, all right, and no friction. All right, so we're going to do the simplest case. So we have Newton's second law for a spring. All right, so we have F equals ma. The F is minus kx equals m. A is the second derivative with respect to time. And we're going to let x equilibrium equals 0, just to make it simple. So we'll set up our coordinate system such that the equilibrium position is 0. So I have this, minus k over mx. So here's the equation. That is what is called a differential equation. It's not an algebra equation because it has derivatives in it. So that means we don't solve for x like it's some kind of constant. We solve for a function. X is a function of time. All right, now we're going to do a little exercise here. So I have a bunch of, when we have a differential equation like this, there are 2 or 3 ways of solving it, but this one does not fit the easiest ways. So when physicists have an equation that they don't know what to do with, what do you think they do? They guess the answer and see if it works. I have 8 guesses over here. I want to know which ones of those work. All right, so each of you have a letter. Your goal is to say, does your letter, does this solution, does it work? How do you do that? You take 2 derivatives and see if the 2 derivatives equals minus k over m times x. Somebody in the room should have told me I made that mistake. All right? You're not on your toes. So I want to know which ones of these, and there may be more than one, work. All right, we're going to do this. So does A work? No? No? A does not work. Does B work? Does it work? Does it work? 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 All right, you can sit down. How about C? Does C work? No? No? All right, you can sit down. Does D work? No? No? All right, you can sit down. What about E? Does E work? E works. All right, if I take a derivative, I get this, a cosine times square root of k over m. And then I take another derivative, I get minus the sign times another square root k over m. So I get minus k over m times the original thing, which is exactly what we want. So this is OK. These are no good. All right. What about f? All right, does f work? Does it work? Work? Everybody agree? All right, so that works too. What about g? Does g work? But it does not work. Take the derivative of the tangent, you get what? Cosecant squared or something like that? Take the derivative of that, you get some mess. All right, you're not going to get back. Does h work? So that's my x. V will equal minus a omega, not omega, minus a square root k over m times the sine square root k over m t plus b square root k over m times the cosine square root k over m times t. Everybody agree? Is that v? Did I do it right? All right, now I'm going to do a. Take another derivative, I get minus a k over m cosine square root k over m t minus, because there's a cosine there. And I get another square root k over m coming out. And I can factor out minus k over m, and I'm left with a cosine plus b sine. That's what I had before us. So it works. So h is good. All right? So notice there are many ways of writing the answer. I could write it even more ways. We can write it, there's ways of writing it using imaginary numbers, for example. And actually, in advanced courses, you usually do that because it's easier. All right? So h is good, e is good, f is good. Which one do you use? Well, you use whatever one you want. Some problems, it makes it easier to use one over the other. In this course, we're going to use, I guess, f is the one that the textbook uses. So I'll stick with that. All right, so we'll just use this. And we usually write it like this, where omega is the square root of k over m. So this is the angular frequency. It is not called the angular velocity. Now notice that if omega t changes by 2 pi, then the change in t called the period t, because if I add omega t plus 2 pi, I get back the same thing. So this means omega t equals 2 pi, or t equals 2 pi over omega. And this is also called 1 over f. All right, so sometimes you're given the angular frequency, omega. Sometimes you're given the period t. Sometimes you're given the frequency f. They're all different, but they're all related. All you got to do is remember this. So on a plot, if I plotted x versus time, you know, I might get something like this. This is the period t. Right, so that's the period t. The fact that it doesn't start at 0 or maximum means that there's some value of phi that you'd have to figure out. All right? So the amplitude A is this size here. This is the amplitude. And phi is determined by the initial conditions. All right? Sometimes you're given the initial value of, you have to be given the initial value of x and v in order to get both a and phi. All right? So a and phi come from knowing the initial value of position and velocity. So notice the following. What's the velocity as a function of time given this formula? All right, so I have minus omega a sine omega t plus phi. Everybody agree? That comes from taking a derivative of this. So we have the kinetic energy, and we have the potential energy. All right? All right, somebody tell me what the kinetic energy is. There's got to be a half there, right? And what else? Yeah, but what is it using this? Good. Omega squared, a squared, sine squared. Omega t plus phi. All right, what about the potential energy? Remember, what is the potential energy of a spring with spring constant k? Yeah, so it's 1/2 kx squared. So I have another 1/2. I have a k. And what's x squared? Over there. A squared. All right. All right. So I want to add those together. Notice from this here, this implies that m omega squared equals k. So I'm going to replace this k by m omega squared. If I do that, I can add them up, and I get the total energy. I get a half here, and another half of the same thing there. So I get m omega squared, a squared. And then I get times sine squared plus cosine squared. But what's sine squared plus cosine squared? 1. So this is the total energy. Do you notice anything interesting about that result? What does it depend on? Does it depend on time? Yeah. Is there a time in this formula? No. So what is that an illustration of? Conservation of energy. The fact that it does not depend on time means that energy is conserved. Right? We already knew that because the spring is a conservative force. There's a potential energy. So energy is conserved. Somebody finally said there is an error, because I can't just add a half plus a half, because I have sine squared plus cosine squared is 1, but I still have the half. All right, so now we're going to show you a bunch of other cases. They're all pendulums, basically, that give you the same kind of result. All right? So we're going to look at a pendulum. Pendulum. And I'm going to do kind of the general case of an arbitrary pendulum pivoted here. And there's some angle theta over there. Okay? So that is, and it has a total length L, and the center of mass is located right there. So this is R center of mass. So the center of mass is there, the total length is L. All right, so there are many ways of doing this, but because we have a rigid object, I like to use torque rather than anything else. All right, so the torque equation, tau equals I alpha. And I is the moment of inertia about this point. I'm going to use this point. So this is my pivot. So I'm going to take I about that point. Alpha is the second derivative of theta with respect to time. Okay, everybody got that? All right, we'll worry about what I is later. What's the torque? So what forces are on that rod? So there's gravity. Where does gravity act? Center of mass. So that's mg. M is the mass of the pendulum. Are there any other forces on that rod? Supposing the rod was just sitting like this. Are there any forces on that besides gravity? Friction, where? At the pivot. There's some force here. It could be friction right now. I guess it is kind of like friction, right? Because my hand is pressing on it. But if I had a pin going through here, it could be some kind of normal force. Okay, so there's some force at the pivot. What is the torque about the pivot due to that force? 0. Why? It's on the pivot, right? The moment arm is 0, right? There's no R in the R cross F. R is 0. All right, so the only torque is due to gravity. So let's see what it is. It's mg, and then it's got to be, the moment arm is R center of mass, right? Is that it? So look at it. At this point here, this is the angle theta. Is this moment arm, is it parallel to mg? No. Is it perpendicular to mg? No. So what do? How do we handle that? What? We use the cross product. So what does that tell us? How do I fix this? We have sine theta. All right. Now, if I'm over here, which way is the torque on the object? Is it trying to make it go this way or this way? It's trying to make it go this way, right? So it's always opposite to the angle. So here the angle theta, if I take this angle, usually I would call this the positive theta. So this is a negative theta, so this has to be positive. So I have to make it a minus sign there. In other words, it's opposite to it. All right? If you don't believe me, think about it for all possible angles theta. What do I do about I? How do I calculate the moment of inertia? We can't say anything until we know something about the object. So I'm just going to leave it at that. I'm going to leave it there for the moment. Now, what I'm going to do now is I'm going to do what's called the small angle approximation. Small angle approximation. This is extremely useful. It says the sine of theta is approximately equal to theta. It's very commonly used in physics. Because if I look at this pendulum, it's going to oscillate at small angles. And this is pretty good approximation. All right, so the result of this is I can write d squared theta dt squared equals minus mg r center of mass divided by I times theta. Okay? Did you notice anything about that equation? Compare that equation here with this one over there. They're exactly the same kind of equation. So that implies I can immediately write down theta as a function of time is equal to some amplitude times the cosine of omega t plus phi, the same as before. Okay? Where omega is the square root of mg r center of mass divided by I. And that's the answer. So somehow you have to compute I, and then this will be the angular frequency. Notice omega is not d theta dt. The angular velocity actually depends on time. The angular frequency is just a number. Okay, so don't confuse d theta dt with omega. They're different things. All right? Now let's do some simple examples. So a simple pendulum looks like this. Okay, so we have M and L. Right, the string is massless, very light, and we have an object at the end, M. Okay? In this case, what is our center of mass? What is it equal to? Where is the center of mass? Where is it? Is it here? Is it here? Is it here? Where is it? Where? It's at the bob or ball. All right? For some reason, they call this a bob. I don't know why. All right? So our center mass equals L. What is the moment of inertia about this point here? What's the moment of inertia about this point here? M what? ML squared. Right? Because all the mass, we'll assume this is small, is all right there. All right? So this implies omega is the square root of G over L. Okay? You may have seen that before. All right. There's also another kind of pendulum called a torsional pendulum, where you have something like this and you twist it slightly and it oscillates back and forth like that. These are actually pretty useful in certain measurements. All right? You get an answer that looks like, looks like this, where you have a torsional constant K divided by the moment of inertia of the thing. So you can read about that in the text. Let's take a look at this and just get a little feel for it. How does the frequency depend on L? right? So L, the length of the thing, we would expect different frequencies. Let's see if we can see this. All right, now I'm going to do this. So the frequency was bigger or smaller as I made L smaller? Frequency is the opposite of the period. The period went up when I made L smaller, is that right? Did I do that right? So I can't do it exactly with this. Why not? Because I have to worry about this, the center of mass and the moment of inertia. There are all those issues. So this is not a good example. Do we have a regular pendulum here? I guess not. All right, so you could put an object at the end of a string and see if the period gets longer or shorter with the length. If this is the frequency goes down as the length goes, no, the frequency goes down as the length goes up, so the period would go down as the length goes up. I think I got that right. Okay? All right.